Hello class, continuing on with chapter 11, I'm going to talk about radical initiators. An initiator starts a free radical chain reaction. Okay, again, an initiator starts a free radical chain reaction. Now, basically, we'll look at a couple examples here. But the lower the enthalpy, we have to break a bond, the easier it is to initiate the radical reaction, okay? The lower the enthalpy, the easier, whoops, to initiate the radical reaction. Okay, so we're going to take a look at a couple of examples here. We're going to take a look at using Cl2. Again, how do you get that to come apart? Either heat or electromagnetic radiation. And we're going to end up with two chlorine radicals, right? Now to get the two chlorine radicals, you have to break this bond, homolytic cleavage, and delta H here, to break those bonds, is 243 kilojoules per mole. Like that. We're going to take a look at a peroxy radical. Like so, and actually you can draw that in there, my half arrow, all right, again, delta H nu, and then here we're going to end up with two oxy radicals, right, and the delta H for this is only 159 kilojoules per mole. And we're going to take a look at one more, although I'm running out of room down here. And acyl peroxide. I hate this not having enough board space and having to write real large here. Anyway, is that going to fit there? Or should I write it at the top? I'm going to write it at the top. Like so. And you get two radicals once again. Like that. And the delta H for this one, well, before we go further, you're probably already going to guess the delta H for this was going to be lower than this one. Now, why would the delta H for this be lower? Because you'll be able to have resonance stabilization of the radical, right? We could move this around, this to here, move the radical there. So this will be more stable. So delta H will be even lower. And it is. In this case, delta H is 121 kilojoules per mole. Okay? So anyway, these are all radical initiators. We can also have a radical inhibitor, which stops a radical chain reaction. Oxygen actually works well as a radical inhibitor. And we're going to take a look at hydroquinone also. But hold on, let me erase this board. Make some room. So radical inhibitors. Okay, basically stop radical chain reactions. O2, right? Oxygen forms diradicals that terminate radical reactions. Or inhibit it, whatever, however you want to say it. So we look at this, just a simple O2 molecule. Whoops. So there's your structure for O2, right? Well, we can have this in the form of a diradical. Break your double bond and form two radicals, thus diradical. Like that. And so that's an inhibitor. As a result, radical chain reactions won't occur rapidly in the presence of oxygen. Right? We can look at another one. Let's take a look at one more example. Let's take a look at hydroquinone. Again, we'll have a room here. I don't know. And da-da-da-da. I guess I'll try to see if we got enough room here. Ah, crap. I'm just going to erase this. And so I got enough room, otherwise I'm going to run out of room. So hydroquinone. Here's your hydroquinone. Like thus. I'll show you how it works here. So we can say we have our free radical here. In this case, some form of carbon, right? We're going to have a hydrogen abstraction. And we end up with this. Now, there's a couple things going on here. We can do the same thing on the other side, okay? We can have another hydrogen abstraction over here. But however, I want you to know this again is also resonance stabilized, right? Resonance stabilized, this right here. But we can have another reaction on the other side. And I guess I'll draw that also. Again, hydrogen abstraction. Half arrows showing one electron movement. And we end up with this. Right, and then again, this should be resonance stabilized. Let me just draw one real quick. So half this double bond's going to go there. The other half's going to go there. That's going to go there. So you move the double bond there. And we're going to end up with this. right there, okay? And no free radicals, right? They're all gone. So anyway, radical inhibitors, right? Inhibit or stop free radical reactions. Now let's go back to our halogenation. Let's look at halogenation in more detail. If you noticed, or maybe even cared, you would have recognized that we've only been using chlorine and bromine so far. We're going to look at why don't we use fluorine and iodine. We're going to see fluorine ends up being too exothermic, and iodine actually doesn't have a negative delta G, but we'll come to that. Halogenation, thermodynamics. All right, we're going to see again fluorine, halogenation with fluorine is too exothermic. And I've told you that in the past. That's why we usually don't use fluorine. In this particular case, that's why we use fluorine usually at all. But in this particular case, we don't use iodine because iodine, again, delta G turns out to be positive. Basically, delta G, whoops, is greater than 0, okay? And we're going to see here momentarily that, yeah, I'll just leave it at that, right? So delta G greater than 0 is non-spontaneous, right? Delta G less than 0 is spontaneous. So this is why we don't use these two in radical halogenation. That's why. But let's take a closer look. If we have delta G is going to equal delta H minus T delta S, right? So we have the two terms here, okay? Again, delta H, that's going to be bond breakage, bond formation, etc. And here we have the change in enthalpy, right? Well, for radical halogenation, we're going to see that delta S is approximately 0. So if we have CH4 plus your generic halogen, again, add some UV light or whatever, electromagnetic radiation, and we're going to get our halogenation, right? Now, how many molecules are on the left side? 2. How many molecules are on the right side? 2. So basically, delta S is approximately 0, okay? So this term drops out, and basically we're going to have delta G is going to be proportional to delta H, the bond breakage information. And I hope my coffee cup is not in the way of the board. Okay? So long story short, again, delta G is approximately equal to delta H, which is going to be bond breakage information. So let's take a look at the specific examples of each one and see what this looks like. So again, I'm going to write each one of these out. We're going to have delta H for this. And as I told you, this is very exothermic. Negative 431 kilojoules per mole. Again, too exothermic. For fluorine. Fluorine is too reactive. Let's take a look at chlorination. Delta H for this is going to be negative 104 kilojoules per mole. Now again, remember, delta G equals approximately delta H, right? So both these reactions would be spontaneous, right? But that one's 4 times more energetic. So you get bromination. Delta H here is only going to be negative 33 kilojoules per mole. So again, remember, delta G equals approximately delta H. So this reaction is still spontaneous, but not as spontaneous as the chlorination, right? Let's take a look for iodine. Here, delta H turns out to be plus 55 kilojoules per mole. So this one again, delta G is approximately delta H, right? So this is non-spontaneous. Okay? That's why we don't use iodine. Again, fluorine's 2 exothermic, iodine's non-spontaneous. That's why we don't use those in radical halogenation. All right, let's see here. Let's take a look at regioselectivity. Halogenation regioselectivity. Right, so now we're talking about chlorine and bromine. We've already talked about the most stable free radicals, right? You have hydrogen abstraction. Tertiary is the most stable, followed by secondary, followed by primary is the most unstable. So that already tells you something about regioselectivity if you're thinking, which hopefully you are. Let's take a look at here. Or maybe you don't really care, but whatever. So here we're going to have